Okay, so right triangle similarity theorem. Starts off with a right triangle. That's right. That's right. Okay. And here's what happens. I'm going to draw an altitude from the right angle to the hypotenuse. So that is a right angle as well. Okay? And now, if you look really carefully and think about it for a minute, we have 3 right triangles. Can you see all 3 of them? The original, right? And then we got that one there, and then we have this one here. Okay? And my proposal to you guys is all 3 of those right triangles are similar. They're all proportional. What do you think? Does it look like they might be? So they're different sizes, of course, but you know we've got this big one, the original, and then we've got this kind of medium one, and then we got the little baby one. It's like the 3 bears story of triangles, and all 3 of them are similar to one another. So if the altitude is drawn to the hypotenuse of a right triangle, then the 2 triangles formed are similar to the original and to each other. Ugh. Okay. Now, I'm going to do some labeling here. See, if I look at the big triangle, see how this is the short leg? And this one is the long leg, and then, okay. But if I look at the little triangle, then what is this one? It's the hypotenuse. And what's this one? The long. So it kind of gets a little complicated. But let's do some stuff here. Let's just call this S for short leg. Call that capital L for long leg. And call this capital H. So we've got S, L, and H in the big triangle. You with me so far? Oh. Tyler, don't sound so excited. Easy. Okay, so think about this. The hypotenuse of the medium-sized triangle. It's L. It's this one, isn't it? The hypotenuse of the little triangle. Huh? S. Okay, maybe I better call this an altitude. That's this one right here, isn't it? Or is it the short leg? Is it the long leg or the short leg of the medium one? It's the short leg, but on the little triangle, it's the long leg, isn't it? Okay? And then I guess we could call this little bit here X. That'd be this guy. We can call this Y. That'd be the long leg. Okay. So, why does any of that matter? Here. What does L over S equal? What does it equal? Over little h. And it also equals what? Little h over x. All these are proportional, aren't they? How about h over capital S? What does it equal? L over little h and Come on, you can do it. Okay. So we have all these relationships. All these relationships here. Okay? So, how can we use them? How can we best use them here? I'll give you one to think about now. So, here's a house. Here's a roof line of a house. It's not exactly the same on each side, but this is 5.5 meters, 3.1 meters. We'll just call this H. From here to here is 6.3 meters. Do you think there's any way we could find from here to here? What, Michael?
Use the Pythagorean theorem to figure out little h, and you can use that and
You guys think you can figure it out? You seem pretty confident. All right, do it. Just that little bit. And I actually stopped right here. Well, I just stopped right here for a second because I didn't label the hypotenuse of the big one. Did you notice? I drew all three. They're not exactly to scale, but I do have the big one, the medium, and the small. And I know this is H, this one's X, this was 3.1. On the medium triangle, the short leg is H, the long leg is 6.3, and the hypotenuse is 5.5? That doesn't work, does it? Let's change that. Let's make this 6.3 and make this one 5.5. Okay, and then how long is the hypotenuse of the biggest triangle? Okay, yeah, I'm going to say x plus 5.5. That works. Now remember, we only need to figure out x, right? So I think we can do it just right there, can't we? We don't really. Got these two triangles that are similar. Do we have a key? Do we have something where we can find a scale factor? Which two numbers are the important ones right here?
6.3 and 3.8.
Those two? 6.3.
Well, no, because didn't we switch those?
How about 5.5 and 3.1?
Well, you're supposed to switch back.
Yeah.
Yeah, you have to.
Oh, wait. I got to switch that one.
Yeah, switch those.
What does this one have to be?
6.3 and 3.
That one's 6.3,
And that one's
and this one's 5.5?
6.2.
Okay, that's better. I should have just made this 6.2, then it would be in nice, easy proportion, wouldn't it? Can you guys find any proportion where you only have one variable?
You can find H, but then you have to go back and find X.
So you got to find H first, don't you? Okay, so this H over, how do you want to do this? 5.5 over H?
Yeah.
What does it equal? This still can't be 5.5.
Yeah, 6.2.
God darn it. You just try this again. All right, new problem. I want to change how I do this. "25 feet, 60 feet." We'll call that H. Then maybe what I'll do is I'll give you this whole thing. 65 feet. That's the whole thing. Yeah, let's try that. What do you guys think of that one now? Notice this bit here. I didn't know what these two were, so I named that one X and I named it Y for a second. And then I thought, I don't want to name this X and Y. That'd be two variables, wouldn't it? So if I name one X and the other one 65 subtract X, I get them both named, but I only use one variable. Okay, so you guys see how we could find this H right here?
Yeah.
Can we find it using those two?
Yeah.
H over what?
20.
Wait, H over what? How do you want to do it, Cheyenne? H over 25 equals, you want to go 65 minus X over 60?
No, 65.
Okay, wait. 60 over 65. Okay, we can find H right there, can't we? And then, of course, this H and this H are going to be the same, aren't they? And then, if you know that H and you know that 25, can you find that X just using the Pythagorean theorem? Yeah, or we could say like x over 25 equals 25 over 65. Can we do that? Mason, got to put your mask on. Is this kind of a pain in the butt, drawing all three of these triangles and then trying to get them all labeled? And Cordell's like, yes, it is. It's horrible, isn't it? Okay. Would you like to know an easier way? Okay. Let's talk about an easier way. So it turns out there's something called the geometric mean. You guys ever heard of geometric mean before? What does it sound like to you guys? Mean. What does that remind you of? Average. Okay. And it's sort of like that, but it just relates the relationships here. So this altitude right here, it happens to be the geometric mean of this part of the hypotenuse and this part of the hypotenuse. And what that looks like is, if h is the geometric mean, what I do is I set up a proportion and I use h twice, like that. And it's the geometric mean of A and B. Which means if I have a right triangle and we draw this altitude to the hypotenuse, if I know two of the three, can I find the third one? So if I know h is a 5 and a is a 7, can I find b? I can't I? Okay, I can just plug in h, and it doesn't matter. It doesn't matter if it's here and here or like this, as long as they're opposite. You got one on top, one on bottom. Then a is 7 and b is we don't know. Can we find b? That's going to be easy, isn't it? Okay. All we got to do, in fact, I wouldn't even cross multiply here. I just multiply both sides of the equation by 5. So these cancel and we get 25 over 7, which is a perfectly fine answer. Okay. Let's say we don't know h, but I know that's 7 and this one is, we'll just say it's 5. Okay. I can still find h. Now I'm going to have the variable h in my equation twice. So in my proportion, I'm going to use h and h, but h is the geometric mean of 7 and 5. So now if we cross multiply, what's h times h? Equals 35. Then what? How about radical 35? Will radical 35 simplify?
No.
It's just 5 times 7, isn't it? So we don't have anything to pair up or anything like that. So radical 35. It's radical 35. Okay? So that's a whole lot simpler than trying. Now, if I were to draw all three of these triangles separately, then, or even the medium one and the small one, here, maybe I can, here. So we've got our big triangle, and we drew the altitude in, and we called it h, and we called this one a, and we called this one b. So if I kind of redraw this, so we've got the big triangle, we got the papa triangle, we have the mama triangle, then we have the baby triangle. Maybe we'll just concentrate here with h. Where does h show up over here? I know it's that one, isn't it? And on the medium triangle, it's the short leg. Okay, and then what's a? Yeah, the long leg of which one? The medium of the mama triangle. And what's b? The short leg of the, that's right, the baby triangle, right? Okay, so with just this, Do you see how A over H equals H over B? Okay? So this is always true. And so H is the geometric mean of A and B. H is the geometric mean of A and B. Now you can say H equals the square root of A times B, if you want to just get right to the point. Isn't that true? You cross multiply, you have H squared equals A times B, then you take the root of each side, and H equals the square root of A times B. I usually think of it as the geometric mean, but whichever. Okay? So now, when I give you a problem, here, triangle, right triangle, altitude drawn over there like that. This is 8 units long. This one is 6 units long. Can you guys find x? Find x and give it to me as a simplified radical. Write the proportion with the geometric mean proportion and solve that. Doesn't take very long, does it? I just think, okay, 8 is the geometric mean of 6 and x. So I suppose 6x equals 64. Is 32 over 3 an okay answer? You okay with that? Good enough. Okay? Here, let's make things more interesting. A little more interesting. Can you find h? Come on, write out the proportion. I hope you're all saying h is the geometric mean of 20 and 5, right? So h squared equals 100. What does h equal? 10. Okay? Equals 10. So that's not so bad. Okay, ready for the bad one? Mason is. I want you to find x. Are you running into any difficulties? Or is it just straightforward? No answers, but you all looked a little ticked. What are you thinking? What's the problem? Does anyone just think they got the answer? Cheyenne? Did you see a difficulty and solve it? No? You didn't see? God, I see a major difficulty. See, because 9 is the geometric mean of what?
X is 50 subtracted.
Oh, so you didn't think that was a difficulty. You just said this is 50 subtract x, and so 9 is the geometric mean of x and 50 subtract x. You all did that fine. And we've talked about that a lot, haven't we, where we name something using the same variable, right? Okay, so 9 is the geometric mean of x and 50 subtract x. So 81 equals 50x subtract x squared. Right? Okay, so here's the problem. This is a quadratic equation. Solving this equation is going to be a bit of a thing. In fact, I would probably add x squared to both sides. I'd subtract 50x from both sides. So I got it to look like that. And then solving that, yeah, that's not going to be pretty. Do any of you know how to solve a quadratic equation yet? Yeah. So when you're given these problems, you're not going to get any of these where you end up with an x squared and an x. You guys are okay with this quadratic equation, x squared equals 81. You can solve that, can't you? Okay. What does x equal? Positive or negative 9. Right? Although we're in geometry, so do we ever worry about the negative 9? Rarely, because it's usually the length of a side we're looking for, and a negative doesn't make a bit of sense, doesn't it? Okay, so we don't usually worry about that, but it really is a solution. So this kind of quadratic equation you guys are fine solving. This type where you have x squared and x, not going to be good. Now you will get some like this. But what happens here when you try to get rid of x squared from one side of the equation? You see how it's going to subtract from both sides? So that's always nice. So these just cancel out, and you end up with 5x equals 20, so x equals 4. So you will end up with something like that. But you shouldn't end up with any like this. If you do, just stop right there, and we'll just talk about that later. Okay, so that's the geometric mean altitude theorem. Hey, check out the poster up on the wall in the back, between my awesome ship poster and the flag. Geometric mean altitude theorem. Look familiar? Okay, so now there's another one. There's called the geometric mean leg theorem. This one does not involve the altitude drawn to the hypotenuse. Okay? Other than that altitude drawn to the hypotenuse divides the hypotenuse here into these two parts, A and B. Okay? So here's what it looks like. I'm going to just cover that up for a minute. X. That leg right there, this is called the geometric mean leg theorem. That leg is the geometric mean. See, I used it twice. That leg is the geometric mean of the piece of the hypotenuse that's connected to it and the entire hypotenuse. Getting that in your notes, maybe? So the leg is the geometric mean of the entire hypotenuse and the piece of the hypotenuse that's connected to it. I don't know how else to call that. Now both legs have that relationship. So if x is the geometric mean of b and c, then y is the geometric mean. What's it the geometric mean of? A and C. Yeah, it's the geometric mean of A and C. Now I can show you this if I drew all three of the triangles. If we drew out the big triangle and the medium triangle and the little triangle, and the little one is X and B, and the medium one is A and Y right there, and the big one, the hypotenuse is C, right? And the long leg is Y, and the short leg is X. Look at those two triangles. Y over C equals A over Y, doesn't it? Okay. Look at those two triangles. Oh no, which one is it to get to? Yeah. X over B equals C over X. So there's no magic thing about this. It's simply, if you look at all three of the triangles that are all three similar, and you just have that proportional relationship. But rather than having to look at all three of them separately and figure out, okay, how am I going to do this, we can just remember that the leg is the geometric mean of B and C, and this leg is the geometric mean of A and C. Okay? I have a really nice geometric mean altitude theorem poster. I do not have a really nice geometric mean length theorem poster, do I? I need one. Anybody need a little extra credit and have some artistic ability? Find Y. I thought Logan was saying you need to move it down, but he was actually saying it's right there.
Right there, I found it.
Good job, Logan. Agreed? Do I need to worry about y could also be the opposite of the square root of 14? Or is it only going to be positive answer? Right? So if I were just solving this quadratic equation, I would say y equals plus n minus radical 14. They're both possibilities. But since y is the length of the side of a triangle, we don't have to worry about the negative bit. It has to be the positive radical 14. That's it. Okay? Not the geometric mean of 5 and 2, though, right? Okay. That's geometric mean. If you're asked to find the geometric mean of two numbers, say 12 and 27. Okay, I need to find the geometric mean of 12 and 27. Well, the geometric mean would be x, and you just put 12 here and 27 here. So the geometric mean of 12 and 27, you find it like this. So x squared equals 12 times 27, which I'm not going to bother to do. I'll show you why in a minute. So then x would equal the square root of 12 times 27, wouldn't it? Okay. Now here's why I didn't multiply them together. I need to reduce this radical. Okay, and so I need to break it down into a bunch of prime numbers multiplied together. Well, 12 is 2 times 2 times 3. Is it not? And what's 27? Okay. So there's no point in multiplying 12 times 27 and then having to break that big number down as a product of prime numbers into all this. It's easier to break down the 12 and the 27 separately. So then I can just say, well, that's 2 times 3 times 3. Holy cow. 18? So the geometric mean of 12 and 27 is 18. Is 18 exactly halfway between 12 and 27? It's not, is it? 12 plus 27 is 39 divided by 2. It's like 9. It's not the mean. It's not the average of 12 and 27. It's the geometric mean. Okay, so there's a difference. Are your brains full? Yeah? This has been a long lesson, hasn't it?
Yeah, we should just do this on the forum.
We should just do that. Aw, you almost had me again, Chloe. Is it?
Yeah, I got 5 minutes.
I think that might have been the longest lesson of the year. Here's what we're going to do. Well, I'm sure we're going to do some of it tomorrow.